All right, so it's about one, so I got to click the go live button. All right. So thanks everybody. So I have some new students this semester. So I'm Harley, the one that's been talking to you in Slack. And I wasn't here last week just because of some personal stuff. And so this week I'll be here chairing the session. And I'm really excited because we have a really nice talk from Neil Krishnaswamy, who has done some really cool work in programming languages for quite a bit. And I'm really excited about this talk just because it kind of talks about some stuff that's relative to my research and then applying it in a place that I don't know much about. So that I think is really exciting. And then it's also about, things related to sort of GUI programming and stuff like that. And I think the students will find that pretty interesting. So thanks a lot, Neil, for being willing to give a talk. We're really excited to have you, and I'll just let you have as much time as possible. So thank you, and I'll let you take it from here.
Okay, yeah, no, thanks everyone. Can you make me host so I can share my screen? Or whatever you have to do.
Yes, sorry, I gotta click a button. I forgot to click the button. Where is it? This one.
Yeah, no, this is the
There
Zoom
you go.
dance that
You should be
happened.
good now. Yeah. It's like so many things I have to click when I get on this thing.
Okay. Okay.
Yes.
So
Yes. Perfect.
so if everyone can see this. So what I'm going to talk about today is some work that actually has been a long time in coming. So when I was a PhD student, like I was working on program verification, things like core logic and reasoning about programs mathematically. And what I had been working on was a way of combining um, a program logic for reasoning about pointers called separation logic with reasoning about higher order functions. And towards the end of my PhD, my advisor said, this is all very interesting, but do you have any examples of programs where you have mutable state and higher order functions? And I thought for a bit and I said, well, yeah, GUI programming is like this because you have to set all these callbacks and things. Give me a couple of weeks and I'll sort it out. That was in 2008. So 13 years later, we're finally getting close to sorting it out. And I'm going to tell you a bit about some of the work that I've been doing. And not just me, of course, but also some students and collaborators. So I want to name Dima Samosvanchev, who's my PhD student, and Christian Grauland, who was a PhD student and now just finished at the IT University of Copenhagen in Denmark. And so they've really been the ones who've been carrying forward this work. But now I get to talk about it. Okay, so the question that got me started on this line of research so many years ago was the question of how should we program with graphical user interfaces. And if you've done any programming in like JavaScript or in GNOME or on Mac OS with Cocoa, you'll generally agree that it's not a fun experience because you have to set all these callbacks that don't run when you want them to. They run whenever the system feels like running them. Like you click on something and then eventually the computer will get around to running the event handler that you wrote to handle that response. And coordinating all these things is just a really brutal and painful process. So in fact, Adobe did a study on their application for, I think it was the Illustrator program, or maybe it was Paint, not Paint, whatever it's called, the Adobe photo manipulation program, and they found that, like, they were writing all these optimized algorithms for image processing in C++, and they found that that was like a quarter of their bugs, and the other 3/4 all came from like UI bugs where you slide a slider and it doesn't change the right thing. And so this is like a very important but also very problematic programming model we've got for GUIs. And so the question that's been motivating me is like, how should we be programming these things in a way that makes it like less unpleasant and sort of fits the grain of like how people think about these user interfaces. And the slightly silly answer to this is that you should be thinking about monoidal adjunctions between functor categories. And I probably won't have time to explain all of this in this talk, but I hope to get to the point where you think this is not an immediately ridiculous sort of thing to say. And so the question is, like, before we can talk about semantics, we should actually look at a program and see what it does. And so let me write a very small program with a hand-drawn button in something that's sort of like pseudo JavaScript. And so what do we do when you're writing a GUI program today? Well, what you'll do is you will create some widgets. So like right here, I create a button and I name it B. And it has the text "Hello World." And so when you create the button, it'll create a button with the label "Hello World," and then you can modify the button. So here I'm going to set its background color to blue, and then when you run it, you get a button. And if this were not a hand-drawn button, you could like click on it, and then it wouldn't do anything because you haven't attached any event handlers. Okay, so you can see here that this is already like a very imperative sort of interface. So you create a button and then you manually modify all of its properties. And because in an event-based program, these modification events happen whenever a callback is invoked, you don't know exactly when these events are going to be invoked. So this is really the thing that makes the programming model for GUIs a bit challenging. And you can see here that, like, when you're locally working, you set it to red, to blue, and then you make another update and it turns red when you set it to red. And so you have this very imperative model, and you wonder, okay, well, what if something happens in here? And that's like really the big problem. And so how do we tell it to handle events later? And so these GUI programs will have what are called event handler methods. And so you have a button, and it has a method onClick. And what this is doing is it's going to say, give me a function to run when a click event happens. And so you pass it a function. And what this function is going to do is it's going to get some event data, which in this example we're going to ignore, and then we're going to run the SetColor method on it. And so now what's going to happen? So before, well, when you change the color from blue to red, it immediately changed from blue to red. But what happened? What does it mean when I say make it blue and then later turn it red? Well, what that means is that you have to think about the timeline. So this button isn't just like a value in your program. It's something that has like, an extension through time. So at time 0, when we create this button, it's going to be blue. And then, at some later time, when I actually click on the button, that's when it'll turn red. And so what this means is that when you're thinking about like what a GUI widget looks like, you can't just think about its current state. You have to think about like sort of its whole future history. And here's an example. So before I said we're going to have a blue button and then it's going to turn red. But what if I had a button and I initialized it to red? And then I said, okay, well, when it's clicked, I want it to turn red. And so now you're thinking, okay, well, now you've done nothing, Neil. But I want to interrogate this point. So, up here on the top, I've got a program which creates a red button and then says, whenever the button is clicked, turn it red. And then on the other hand, I have a different program which says, I have a button that's red, and whenever I click it, and then it doesn't say anything about when you click it. It just says, I create a button and make it red. And so what's the difference between these two programs? Like what does this line actually do anything? And so, when you just run these two programs by themselves, it doesn't make any difference. Like you have a button, it starts off red, and then at some later time it's still red. And when the event handler says, when you click the button, turn it red, again, it starts off red. And then when you click it, well, nothing happens because it was already red. But these two programs right now, these two programs look like they're the same, but they're not actually. So what if we added one more line to this program? So what if we added a line to the program that said, I want you to set this button to have the color blue. And on the program on the left, what will happen is we set this program to red and then immediately turn it blue. And so the history of this program is going to be, it starts off blue and then it's going to stay blue forever. But on the other hand, over here, we have a program, and we're going to say we're going to create it as a red button. And then we're going to say, whenever you click it, turn it red. And then we say, oh, and by the way, change your color to blue. And so what's going to happen? So at this initial state, this will start off red and then turn blue. And that will be its sort of final state at the time 0. And then later on, when you click the button at this time n, what will happen? Now this event handler will actually do something. It'll turn the button from blue to red. And so what we've got here is an observable difference between these two programs. So initially they look the same, but later on, once there's been some interaction, these two programs are different.
Sorry. So like at T0, it starts as red. So I agree with that. Then we set the handler. Are you assuming that the program executes completely in the same time instance? Or could it really be when it was blue?
Yeah, that's a great question. In Java, so this question of like, does a program run all in one instant? That's actually part of that's something that a GUI API designer has to decide. And in the case of JavaScript, the answer is yes. So if you read up on JavaScript's event loop, they call this like synchrony. So when you run a piece of code, it'll run to completion, and then only after that will you get the next event. So in JavaScript, what will happen is like sort of on the first tick, you'll run this, and then you'll run this, and then you'll run this, and then you'll run this. And so your program will, at the time that it starts waiting for another event, it'll actually be blue. And in fact, most GUI toolkits actually work this way. Except that let me rephrase that slightly. Every GUI toolkit started off this way, and then later on they all added threading support, and the story got a bit more complicated. JavaScript has sort of held off on adding thread support that can sort of see the event loop. So this model is absolutely true in JavaScript, and it's the way that like the designers want you to think in every other GUI toolkit, like on Windows and on Mac and Linux.
Okay, cool. Yeah, thank you.
Okay, so but the point is that like that this program and this program right here, they're not equivalent because we can add a little bit of extra code that can distinguish the two. And the distinction doesn't happen immediately, it only happens later when someone clicks on the button. And so what does this mean? And so what this means is that, like, we look at this programming model and we're going to see two things. So the first thing we saw immediately is that the widgets are stateful objects. So you can call a method like SetColor and it'll turn something blue into something red. And these are like modifications that happen instantly. But at the same time, there's also like a timeline in the background. And so we can also write functions or issue commands, however you think about it, where the updates don't happen immediately. And so you start off blue and then later you turn red. So the mental model of programming has both state and time in the model. And it can be quite a challenging model to deal with, because people are used to thinking about state, and then when you add time to it, it's not just enough to modify an object. You have to think about when it gets modified, and that's something people find pretty challenging, and what I find challenging too. And so the story, and so I've said, so because I'm a programming language designer, I said that we have these two problems. And so when I talk about this, whenever I say there's a problem, what I mean is there's some type system features that can help manage these problems. And so we had this problem of state, or like, how do you represent state in a way that people find easy to think about? And how do you represent time in a way that, like, the computer can helpfully sort things out for you if you make something that's a bit inconsistent. And so, this is really what like type systems are for. We have these constraints we want to check. Like individually, they're not very hard to keep track of, but the difficult thing is keeping track of them globally and without any errors anywhere. And so that's exactly what type systems are good at. And what we've learned is that there's a whole class of type systems called linear type systems. I don't know how many of you have tried any programming in Rust. That has a variant of a linear type system. And so Rust's big sales point is that, like, the type system will automatically check that you're allocating and freeing memory safely, and it has no garbage collector, but it's still a memory safe language, and it uses like a discipline based on linear types to enforce this property. Something that's a little bit less well known is that there are also type systems or logical systems that can help you keep track of when things happen, and so this is what the field of temporal logic is all about. So in ordinary logic, we talk about, A is true. And in temporal logic, we have the ability to say, well, A will eventually be true, or A was true in the past, or A will always be true. So we add some vocabulary for talking about time to our type system. And the idea behind the work that Christian and Dima and I did was that by being sort of systematic about adding support type system features to support state and support time, we ended up with a nice language for writing programs that care about stateful values extended through time, or GUIs. Okay, so now what I'm going to do is I'm going to show you some basic API features. I'm not going to show you any typing rules yet, but I'm going to show you like the signatures for these functions, and so well, the type signatures for these functions, and I'll sort of explain what's going on here. So what we have in a linear type system is the ability to track when variables are used or not. So in a regular language, if say you have a function, like let me write a function here. So this is in a normal language, you can do something like, okay, I'm going to get an argument x, and what I'm going to do is I'm going to return to you x plus x. So you defined a variable, and then you used it twice. And so this should look perfectly sensible to you. Linear type systems say, on the other hand, that this is not okay. And what they mean by that is that there's a restriction which says that variables can only be used once. So this is this thing right here is not okay because it's not linear. You're using x twice. Sorry, I want to make this black maybe. So you could, on the other hand, in the linear type system, it would be okay to write something like this. So here, x is defined once and used once. Oh, let me make this blue because this is okay. So we have x as a variable and it gets used once, and we have y as a variable and it gets used exactly once. And the reason this seems like a bit of an artificial restriction, but what's going on is that if a variable can only refer to a value exactly once, then what that means is that you have a single point, that in the implementation, you'll only have a single pointer to that object. And so if you have a function which takes in a value, does something to it, and returns you a new value, it'll look like a purely functional program, but you can implement it with mutable state. And your linear type system lets you ensure that you never get two inconsistent views of that data structure. And so this is and let me carry on a bit more. So the way that people write these things is this normal function type is it takes an input and gives you an output. And with a linear type system, you say, well, okay, I'm just going to write it as a lollipop. People actually call this lollipop. So this means I get an X and I can only use it once when I'm producing a Y. And so what does this new widget signature here say? It says, if you give me no arguments, what I'm going to do is I'm going to give you a widget back. And so what we've got here is a linear function which creates a piece of state. So we call the function, the widget, the new button or new tab function method is invoked, and that value is returned back to you. And so likewise, when you're done with it, you can say, I want to take the widget and get nothing back. And you can implement it by freeing the memory associated with this widget here. So we're able to create and destroy values with an imperative implementation, but a functional interface with this kind of linear function type. And one thing we'll end up needing is the ability to name specific widgets. And to do this, we'll index all of these widgets by a static name representing what it is. And so when you call new widget, you get back a widget, and you also get back like a compile time ID for that widget. And the free widget says, well, if you give me any widget with any static ID, I'll be happy to destroy it. And so in order to be able to talk about these static identifiers, we also introduce quantifiers from logic. So we quantify over the static IDs. And we'll also quantify over time a bit later. Okay, so yeah, I guess I could have said what's going on. Oh, yeah, we'll go on. So the linear function space from linear logic gives us the ability to talk about creating and destroying state. And there are certain operations that we'll want to do where we need to know statically that, I have the widget at time 0 and the same widget at time 1. And to check that statically, you need to have like a unique identifier for each widget in your program. And so we introduce these static IDs, and to manage them comfortably, we need the quantifiers. Okay, so now if you look at a method like SetColor, what does it do? So it says, well, what I want you to do is I want you to give me, say, an enumeration for the color, and then give me a widget, and then I will give you back a new widget with the color that you told me to. And so this thing here, so a color is like, well, it's going to be a string in JavaScript describing a bit of CSS. In other toolkits, it'll be an enumeration with the appropriate color. And so that's a value you're allowed to use as often as you like. The restriction that you must use each value exactly once, that's a very restrictive thing. So if we applied it to everything, we wouldn't even be able to write a square function that takes x and multiplies it by itself. So there's only certain things that we want to be able to treat linearly. And so some values we want to be able to use as often as we like, just like normal. And so these are what we'll call the intuitionistic values. And then other things which are linear, other things which are stateful, we want to treat them linearly. So here we'll say, okay, this looks like sort of state passing style, where you get a value and then return an updated value. And from the programming point of view, that looks like normal functional programming. But we can implement this because this is a linear function with a mutable update. Okay, so so far we've created widgets. We can set their color. How do we talk about when things happen? And so here we're going to diverge a little bit from the JavaScript APIs, because the JavaScript APIs are higher order APIs. They say, give me a callback function. And I teach a lot of functional programming, and higher order functions are actually a tricky concept that people struggle with. And so it would be nice if we could not do that. And so the trick that we're going to use is we're going to adopt an idea from temporal logic. And so what we're going to do is we're going to say, what does an on-click mean? It means that you ask the widget when something happens, to notify you when something happens sometime later. And so for our click, what we're going to say is, give me a widget. Whoops. Give me a widget, and then I will give you that widget back. And I will also give you a token that'll be ready in a while. So this little diamond A is a notation from temporal logic. And what it means is eventually A. So well, in this case, it means eventually you'll get a unit value. So if something having a type of integer means that you have a 5 or a 6 or a -13 in your hands, and eventually integer means that you don't have an integer now, but you have a promise that eventually you're going to get an integer. And so for a click, you don't actually care much what data comes along with it. The click, the only information is that it happened. But if you press a keystroke, what you'll learn is a character that you get eventually. So when you ask for an on key press event, you don't get the keystroke, you don't get a character immediately, you get it eventually whenever the user actually decides to push something on the keyboard. And so what this does is, we'll need to introduce some new programming constructs to use this diamond type. But what'll end up happening, I hope, is that you get a sort of more direct style of programming than the indirect callback heavy style that we're used to from GUI toolkits like JavaScript. Okay, and so now now let's talk about how would you use such a thing. So we have a key press, we've gotten something that's eventually going to be a character. What do we do with it? And the idea is that if eventually you have a value, well, that means at some specific time it's going to exist. And so we're going to introduce one more connective to talk about time. And this connective is the at connective. And you should read this. So if diamond A means eventually you're going to get an A at t means at time t you're going to get a value of type A. And it turns out that this diamond, that the diamond and the can be encoded using the at. So if you have something that you get eventually, then that means that there exists a time at which you'll have the A. And if you know that at a particular time t you're going to have an A, that means that eventually you're going to get an A. Okay, so why do we want these two notions? And the answer is it ends up making the implementation easier. So this thing here is the primitive concept. At a specific time an event happens, but it turns out that for programming, for implementation purposes, like being able to be non-specific about when an event happens turns out to be really important. And the reason for this actually has a lot to do with the implementation of GUIs. So there are certain programs like video games where something is happening 60 times a second. So like, an alien is shooting a machine gun at you. At every frame, there should be like, a new laser beam or explosion or something. But but most applications are not like this. So if you open up Emacs or Word or VS Code or something, like what that application is going to do is most of the time it's going to spend waiting for you. Most people cannot type 60 characters a second. I don't want to say, well, in fact, no one can type 60 characters a second. I'll be absolute about this. And so most of the time, your program is just going to wait for you to type something. And if you're doing something like programming, you're not even going to be anywhere close to your maximum typing speed because you're going to be thinking about what your program does. And while you're thinking, your program is waiting for you. And so you want to be able to talk about things happening eventually in order to permit the implementation to go to sleep. Okay, but what do we do with these temporal connectives? And so now let me go back a little bit. I want to show you this picture again. So over here, what we saw was that widgets have a value that's extended in time. So this widget right here at time 0, it's blue, and at time n, it's red. And so how do we talk about having a widget at time n? And so what we're going to do is we're going to say that if you have a widget, you can break it into 2 pieces. You can break it into the piece running from now until time t, and then you have the remainder of the widget starting at time t. And similarly, if you have like the beginning of the widget state, and you know that later on you can reconstruct the whole widget, you can put it back together to get the widget back. So what you should do is you should be thinking about a widget as having a stream of states. So like this widget right here, at time 0, it has a state I0. At time 1, it has a state I1. At time 2, it has a state I2, and so on. And so now, when we call split on this thing, what we're doing is we're dividing the history of this widget, this stream of states, into 2 parts. We're dividing it into the beginning, running from time 0 to t-1, and we also have like the suffix, which is the widget starting at time t. And so, okay, so why do we want to be able to split the stream into pieces? And the answer is that this is exactly what we'll use in order to write programs which do things at certain times. And so what I'm going to do now is I'm going to show you what a program would look like with this API that I've been talking about. So what I want is a little widget which has a number in it, and every time you click that button, the number that it's displaying goes up by increments by 1. So this is like one of the very simplest GUI applications. And so how do we write this? Well, we want to keep doing something, and so we're going to do this by defining a recursive function. And so we're going to get our widget, and we have a number to start with, which is like sort of the current state. And so what's the first thing that we do? Well, the first thing that we do is we're going to update the text of the widget so that it has like it's like displaying the correct number. And now what we're going to do is we're going to wait for a click. So we call onClick on W of 1, and we get this E here. And this E has the type diamond I. And now when we call out on it, so out of E, this thing here is going to have the type exists I unit at time I. Sorry, I just want to check with everyone. Is what I'm writing legible, or should I use a darker color?
On my end, it looks good.
Okay. Okay, so now we know that we've got this unit value and we've got it at time t. And so when we unpack it, we're able to get like a time t, okay? And we say, okay, and we have this unit at time t. Okay, fine. So now we know what time statically that this widget is going to be clicked. And so what do? Well, we say, let's split the widget into its part running from now to time t, and the widget state starting at time t. Okay, now we've divided our widget into two pieces. So right here, we're going to have like our prefix. And it's going to run from time 0 to t-1. And then we'll have a widget that starts at t and keeps going on until it gets freed or whenever, like the whole rest of its life. And so now think about what this program is supposed to do. What it's supposed to do is at time t, its number is supposed to go up by 1. So what can we do? So what we can do is we can say, okay, call this function recursively on W3 at the time t. And so now what'll happen is when you make this recursive call, it's going to increment the label right here at this time, and then it's going to wait for the next click. And so now that we've modified this future state of the widget, we can put it back together and we get back our widget. Only now it's waiting for clicks, and it'll count up by 1 every time you click on it. And so there's no callbacks at all. All we're doing is we're thinking about a widget as if it's a stream of states, and we're splitting it apart, making a recursive call at the right point, and then putting it back together. So it's turned like programming callbacks into programming with streams or lists. And so hopefully this should be an easier programming model to prove things about, and ideally even an easier programming model for people to actually write programs with. We don't know if that's the case yet or not, because we haven't finished implementing this language yet. Though I'm hoping to do that in the coming year. Okay.
Cool. Hey, Neil, there was one question on YouTube, if you don't mind.
Sure.
What are you able to chat like the Zoom chat? I can this in
yeah,
there.
I can. There. Yeah, if you can paste it in, that would be good.
Yeah, because it has a type. I want to make sure that that's it.
Yeah, that's it there. Okay. Why is widget onClick having a future in the form diamond I instead of diamond widget to widget? Okay, so I can explain that, and this is actually one of the things I'm happiest about. So let me add a page here. Let me just insert something here. Okay, so let me write question. Let me write, where does diamond I come from? Okay, and so this is one of the things that actually makes me the happiest about this line of work, because it turns out that there's this really neat connection between formal logic and how you implement these things. So suppose we have a button B, and you have like a method onClick, or like let's call it onEvent, say, and its type in like I'll use like a ML or Haskell style syntax. Its type is going to be, you give me the events data, and then do something at that time, a callback. And what this is saying is, if you give me a callback that has some side effect, then I will attach it to the correct list of events that's waiting for that event. And so there will be another side effect. And so the thing I want you to note, so let me do a little bit of talking about temporal logic. So in temporal logic, we have this notion of diamond, which is eventually. And there's also in temporal logic, there's also this connective diamond A, which means always A. And so what diamond A means is that you have a value that's good to use at any time in the future. It's not restricted to the current instant. And so if you think about a event handler, you don't know when this callback you don't know. Why is this not showing up? Oh well. You don't know when this event handler is supposed to happen, so you have to be ready for it to be fired at any time. And so its type is secretly like always give me a handler that's ready to fire at all times in the future, and then I'll attach it somewhere and invoke it at the right time. And okay, so what has happened so far? And the answer is nothing has happened except that I've refined the types to be a little bit more informative. And now, if you've done much functional programming, types like this should remind you of something called continuation passing style. And continuation passing style, or double negation style, is a way of thinking about logical negation. So erase all this. So let's encode like not A as A arrow IO unit. And so now this type of on event is going to be this thing here is going to become not event. And so we have box not event. And then this thing here is going to give us another not. So the type of our callback is really b.onEvent has the type not box not event. And in temporal logic, this is exactly the De Morgan dual. So box and diamond are exactly De Morgan duals. So what's happening in our implementation is that there actually are callbacks everywhere. It's just that you never actually see them. And this isn't only like, sort of pure logic. If you do GUI programming in JavaScript these days, what you'll find is that people will tell you to use promises. And promises have almost exactly this this structure right here, where where the callback becomes implicit. And they have the syntax for async and await that lets you never write a callback, even though the code is in a callback heavy style. And that's exactly what's happening with our diamond. So our diamond is secretly something that's waiting for a callback, and all the operations that I have for manipulating these eventualities are building up event handlers that are going to eventually actually do something. And so this is actually one of the things I'm happiest about, because the formal logic and the implementation like really line up perfectly. Okay, and yeah, okay. So here, this is the that same example as before, but I've labeled the types of everything. I think I did that before, but I'll stop here to see if anyone has any questions, because I know I just threw a bunch of code at you. Okay, I don't hear anything. So please be aware that I can't see you. All I can see is my slides. So please don't feel shy about asking questions or piping up.
Yeah, no, I thought
this is
pretty interesting.
pretty interesting. And
one thing it reminds me of is it's kind of like what you're doing is giving a typing to reactive program.
Yes, that's exactly right.
Okay, great.
So this is well, I guess I can tell you a history story now. So this actually turned out to be the big problem that I had when I started working on correctness of callbacks and GUIs way back when. And the problem was that, like, when you say I want to prove this program correct, you have to answer the question, what does correct mean? What do you want the program to do? And and I realized I had no easy way of answering this question. And so that actually led me into doing a lot of work on reactive programming. And the 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 so basically, I ended up a while back with, like, a very good language for doing reactive programming for sort of highly interactive systems where something changes on every tick. And it was like a good fit for things like video games, but it was a bad fit for things like text editors or spreadsheets or things like this, where most of the time nothing is happening. And so this particular line of work came out of thinking about how can we make reactive programming work well for these sorts of GUI applications where most of the time nothing is happening. So the ones where you're waiting for a user for most of the time. And so that's why we've been thinking so hard about callbacks and how to have a good type system for callbacks.
Yeah, it's interesting.
Yeah, it's interesting, and
Because
because
reactive programming is something I've been thinking about as looking for applications for linear and graded stuff. So when you went down, started talking, it was like, oh, this is a lot like some things that I've been thinking about too. So that's pretty cool.
Yeah, no, it really is. So I can, so this let me back up a little bit. Actually, I have this time. So so this A at T thing here, it's like, it really is a kind of graded type.
Yeah. Oh, yeah.
yeah,
I
oh
was
yeah,
gonna
I
ask that
was
question.
going to ask that question.
So like we haven't really thought through all the implications of this. It's something we've noticed, but we don't know what that means yet. But there's definitely connections to linear types and graded types.
Yeah, cool.
Yeah, cool.
Okay. All right. So now what will happen once you actually run this program is that if you create a new widget and then you call count on it, what's going to happen? It's going to get initialized to 0, and then every time you click the button, the number will go up 1, 2, 3, and it's not a it's a very simple GUI program, but like the fact that we have like a really nice type theory in which to express it in a nice semantic, denotational semantics for this language is something that's very satisfying. Okay, so I mentioned type theory, and I guess we've gotten at least one question about it. So what is this type theory? And the answer is that what we're using is what's called the linear nonlinear calculus. And it's actually about 25 years old now. So if some of you have seen linear types before, you might have seen like, you might have seen linear types with like this tensor product for pairing things and the linear function space. And you may have seen a funny looking type that looks like this, bang A. And this is the type of A's that you're allowed to use as often as you like. And what the linear nonlinear calculus does is it says, well, with what this bang does is it lets you talk about things you can use multiple times, but in a sort of second class way. And so what the LNL calculus does is it says both of these two things should be on an equal status with each other. So what we're going to do is we're going to have two languages and you can embed programs of one in the other. So we're going to have like a nonlinear type theory. So you should think of this as a totally normal functional language like Haskell or OCaml or something. And then we're going to have a linear language as well. And the trick is that we have a way of embedding linear programs into the nonlinear world, and we have a connective for embedding nonlinear things into the linear world. And these two connectives, if you care about the semantics, they form an adjunction. And the composition of these two things gives you the exponential that people were originally used to. I think Harley has done a fair amount of work on this calculus. Okay, so we have this way of talking about linear and nonlinear types. And what we're going to do is we're also going to add some connectives for talking about time. So we have the eventually modality I talked about earlier, and we also have the at a specific time modality. Okay, so we have the ability to talk about when things happen, and then we add a couple of connectives that are actually about widgets. So we have widgets, and like the beginning of a widget, and then various operations to manipulate these things. And we'll also have like some quantifiers to talk about either widget IDs or the times at which things happen. Okay, so what does this, so I've shown you what a type structure for this language looks like. And we do have quite a few types, but what do the programs look like? And the answer is it's kind of a lot of judgments, and I apologize for this, but they all are sort of end up being necessary. So we had these two sorts for when things happen and widget identifiers. And so we need to say, is this a well-formed term? And then we have like three judgments for talking about programs. And so we have one judgment which says a program is a nonlinear program, which doesn't have any linear terms inside of it. And so this is like the ordinary functional programming typing judgment. And then we have another judgment that says T is a linear functional program. And then finally, we have a fourth judgment, which says that T is a program that gives you an A at time I. Okay, so we have a slightly complicated set of typing and judgments, but the rules themselves turn out to be extremely simple. So for the intuitionistic ordinary functional programming calculus, the rules are the same as always. A variable x has the little x has the type big X if x colon x occurs in the context gamma. And when you have a function lambda x dot e, it has the type x arrow y if you can show that the body has the result type y, assuming that the formal parameter x has the type x. And so these are totally standard rules for the simply typed lambda calculus. The one thing we add to this is the way of embedding linear terms into the nonlinear world. And what we'll do is we'll say that this term t can be used nonlinearly. This linear term of linear type A can be used nonlinearly when t doesn't have any free variables. And if you remember that the linearity restriction is that every free variable in the program can be used exactly once. So what does that mean if you have a linear program that doesn't have any free variables? Well, obviously you can use it as often as you like because every one of its non-existent free variables is being used once. And so sort of closed linear programs can be embedded into the nonlinear world. And the linear typing judgment is a little bit more complicated. So we have a linear typing context delta, and it has two kinds of variable bindings in it. One says x colon a, and that means x is an a right now. And the other one says x colon a, and I put it in bracket I. And this says this is a variable telling you that x will have the type a and I steps in the future. And so most of the rules in this calculus are the standard rules for linear logic. So the variable rule is really like one of the key rules, and it says x has the type a when the linear context is just the variable x colon a. And so in this program x, it only has one free variable. So the only free variables in the linear context can have are x itself. Otherwise, if the delta here had any more variables, those variables wouldn't be used. And what you can see, let me look at this rule right here, because that'll show things off the best, is if you have a linear pair, A tensor B, you divide the context into two parts. One for the A component of the pair, so this is delta 1 for the A component of the pair, and delta 2 for the B component of the pair. And so what happens is that as you go up the typing derivation tree, the variables get routed into different sub-branches of the program, and this enforces the property that every variable gets used exactly once. So like with function applications, we have two subterms, T1 and T2, and the linear variables get divided among the two subterms. Okay, so that's normal linear typing. And then we have to do a little bit of stuff to talk about how you can use these values. So if you have an intuitionistic value that has the type G of A, then you're allowed to run it as often as you like to get a real linear A. And you see, and because this thing up here was built without using any linear variables, you don't need to have any variables in order to call run. And similarly, you can embed intuitionistic things into the linear world. And if you have a value of intuitionistic type X, then you can form a linear value fx that doesn't use any variables. And as I mentioned slightly earlier, like if you've seen linear logic, you may have seen this exclamation point or bang A type, and we can recover that using this LNL calculus. Okay, so how do the temporal types fit into this picture? And the answer is that this thing is a what's called a possibility or a modality in linear logic. In temporal logic. And so what this means is that if you have an A, you can say that you have an eventually A, because you have an A right now, which is the same as an A 0 steps in the future. And if you are able, if you know that you have an A at some point in the future, what you can do is you can use it to form something else that will happen at some point in the future. And so what's going to happen here? So what are we saying here? We're saying I'm going to use up all the variables in my context to form something that will happen eventually in the future. And then I can assume I have an A and calculate with it in order to produce something of eventually B. And so if you think about it, you wait for some number of steps for the A to happen, and then you're saying, well, and then some later point in the future, I'm going to get a B. And so, you know, eventually B is the same as something happening eventually. And one thing you should notice here is that this context is not divided. You have to use all the variables to form the diamond A. And the reason is that all of these variables are available in Delta are available right now. And you don't know what time you get this A. So you can't use any of those variables. And so we omit them from the context over here. And now here comes another thing that I think is really cool. So if you've done programming in something like JavaScript, this thing here is the equivalent of the then method on a promise. So you have a promise of A, and then you say, then when the A completes, do this other stuff. But when you're doing this sort of concurrent programming or reactive programming, something else is going to happen. What's going to happen is sometimes you need to choose between two events. So maybe you know that an A is you know that a is eventually going to happen and B is eventually going to happen. So maybe you're waiting for a click on the mouse or a keystroke. So how do you select between the two of these things? Well, you know that one of these things is going to happen first. So either A will happen first and you still have to wait for B, or B will happen first and you still have to wait for the A. And so what you can do is you can say, I want to select between this event and this event. And if T1, the diamond A happens first, do this expression T3, and if T2, the diamond B happens, then I want you to do this, take this branch T4. So the select operation is going to wait for the first event that happens. And this is part of the POSIX API. And also part of the selection operators are also part of the promise API in JavaScript, and they also have a nice query Howard interpretation. So modal logicians turn out to have the worst naming convention in all of mathematics. All of their systems have like some sequence of numbers and letters. So the modal logic that's about the linearity of time is called S4.3, and I think it's actually S4.3 lowercase I, and it expresses the linearity of time. So select, if you wrote select as a function, what it would say is, if you give me a diamond A and a diamond B, then eventually you're going to have an A and a diamond B, or you're going to have a B and a diamond A. And so this is expressing semantically the linearity of time, and programmatically it's letting you wait for one event to happen first. It turns out to be like having a primitive like this turns out to be the key thing that you need in order to make a reactive programming language that works well with these kinds of with this kind of promise-based style. Okay, and so now the last bit of the type system, and I promise I'll wrap up pretty quick, is that you have a we have to talk about this at a specific time operator. So we say that t happens at a specific time I, giving us an a at a specific time I, when every single variable in delta is a variable at the time I. So what we're going to do is we're going to say this function right here, what it's doing is it's saying it's a partially defined function, and it says that an empty context is sent to an empty context. And if you have a hypothesis x colon a at the time I, we're just going to make it x right now. And then we're going to do the same thing to the remaining free variables. And so what we're doing is we're saying, well, if t has the type A right now in this context delta prime, then we can stick an at I on all of the hypotheses, and we know that the expression is going to have the right type, because t at I is only using the variables at the time I. And if you have something of the type t t has the type a at time I, then when you let bind it to something, you can just add a variable at the time I. So that's how this is how you create those variables, and this is how you use them. Okay, and so that's actually pretty much the entire type system. And so I mentioned earlier that the diamond A, the eventually A, and the A at I are actually redundant. That diamond A can be encoded in terms of the at time. So why do we need it? And the answer turns out to be that if you try to write the type of select using the at primitives, you get a very complicated type with various constraints between timing variables, and that turns out to be difficult to implement. So I didn't implement it, and so we have yes.
Right. You probably have to use. I think my echoing. Do you have your volume as well as your headphones or?
No, I just have my headphones on. I don't hear an echo when you're speaking.
Yeah, I do. Weird. Maybe it's my volume. Let's turn it down. Hello.
I still hear you.
Yeah. Well, anyway, yeah, those remind me of the constraints that get in like Granule when we have to solve typing for graded modalities.
Yeah. So
we use the FMT solver.
Yeah. So this is something that for this language I didn't want to get into.
Sure. Yeah. Sure. Yeah.
But it's like something that would also be, I think, like good to look at. I would actually be really happy if, like, this whole system could be turned into a library in Gradle, because
Yeah.
that would be a sort of a nice advertisement for this approach to type system design.
Yeah. We'll talk about that more.
Yeah. Okay, so it's actually past 7, and my kids will be sticking their heads in through the door.
Yeah.
So I will
finish up however you like.
Yeah. So what I'll do is I'll just sort of skim over the semantics slightly. So the kind of the really interesting thing, like sort of the bit of grit around which the semantics was built, was, what is the semantics of a widget? And so what we did was we said, okay, well, we don't want to try to model, like, having a heap and callbacks and event loops in our semantics. So what we're going to do is we're going to think of all the events that you can actually invoke on a widget. So, like, setting the color, setting the text, things like this. All the operations you can perform on a widget. And what we're going to do is we're just going to record a set of them, like a set of basic events and when they happened. And it's up to the implementer to figure out how to turn one of these bags of histories or whatever into an actual thing you display on the screen. And so we just record all the operations that were ever performed on a widget, and then we add like some consistency relation, which says, well, at the same instant, you can't be both turned red and blue. So this is just sort of recording all the things that happen to a widget. And then now that we have this, the question when you're doing semantics is always to ask, where does your semantic object live? Like, sort of what category does it live in? And so what we noticed was that if you look at temporal logic the way that, like, people in model checking do it, they think of classical logic as being all about Booleans. And temporal logic is just about functions from times to Booleans. So a temporal proposition is something that can be true or false at each time instant. And so basically for our semantics, all we do is we play a trick called crypti-joy-all semantics. So what we do is we take all of these bools and we turn them into sets. So now we're saying the meaning of a type is not a set, but a different set at each instant in time. And there's a few issues with this really simple idea, which is that you can write down some crazy things. Like, you can write down something that says, well, okay, I'm going to give you a type that's going to be a bool at time 0, a string at time 1, a function from integers to floating points at time 2, and there's no relationship between any of these types at any instant. And so we didn't want to do that, because in the actual programming languages people use, there aren't any types like this. And so what we did was we said, okay, we're going to have a model of time in which there's sort of a global element, and then we say a global view of time, and then we're going to say we're going to have a specific view at each instant. And if you do this, then like this issue of, like, having no relationship between any instance goes away. And I won't get into the details of that. And then the other issue is that GUI programs are actually really non-deterministic. When a button is clicked is under user control. And so in this semantics where we say, okay, everything is a function, every type is a family of types, and a function is a family of functions, one for each time, like, every one of these functions is still deterministic. And in an actual program, the GUI programs are not deterministic, because when things happens is up to you, and that's totally arbitrary. You can, like, flip a coin to decide whether you're going to press X or Y. And so what do we do? And so what we do is we take advantage of a really simple observation, which is that when you want to talk about non-deterministic things, it's natural to move from sets to relations. So you can think about a relation between A and B as saying, for every A, I'm going to give you a set of possible Bs. And it turns out that relations actually form a model of linear logic. So, a relation between A times B and C is isomorphic to a relation between A and B times C. And if you define like the linear multiplication as the linear product as the Cartesian product, and you define the linear function space as the Cartesian product, you get a formal model of linear logic. It's sort of a cheap hack, but it really captures this fact that that when things are clicked is under user control. So what our widget functions semantics is that you have a widget related to a widget plus all the times at which an event could happen. And so there's a way of giving semantics to all of these modalities. And let me skip a bit over that, and so that I can wrap up. And so the takeaway point here is that GUI programs are sort of like the most practical programs we write, but they turn out to have a lot of really nice semantics lurking underneath. And it looks like this totally dirty thing with like mutable state everywhere, and like it's not even mutable state everywhere, it's mutable state that's changing on you everywhere.
Yeah.
Whenever you look elsewhere. But it turns out to have like this really neat and nice semantic structure, and it has like really nice programming models that sort of we're waiting for us to discover. So that's really the takeaway. Okay, and so if anyone has questions, like I'm happy to take them now. Maybe I'll turn off my video so I can actually see people.
Yeah.
Okay. Oh, I see a lot of things in the chat. Did you ask all those questions?
Yeah.
Okay.
Yep. Yeah,
Okay.
everything's good, and the YouTube chat's all good. So yeah.
Okay.
Yeah, I think this I noticed the echoing went away too when you switched. That's interesting. Anyway.
Oh, okay.
Some diagnosis in the
Yes.
future.
Yeah, I don't know. I'm using my headphones just to avoid echoes.
Yeah, it's strange. But anyway, yeah, I thought this was a great talk. I have a lot of interesting ideas now. But yeah, this was great. Thank you very much.
Yeah, so if you want to look at our paper, it's I think FOSSAX this past year.
Okay, great. Yeah, I didn't know if you. I was going to ask if you had a paper or if it was still being worked on. Great. Okay, yeah, I'll definitely look at that. Yeah, awesome.
Okay.
Great. Yeah, I think that's it. So thank you very much, and thanks everybody for showing up, and yeah, have a great night.
Okay. Yeah. Hopefully, I'll see you all in person sometime.
Yeah, fingers crossed. Maybe Popple 2022 will be in person.
Yeah, I'll see if we're allowed to leave Rainy Plague Island.
Yeah. Damn.